roll. All right, so we were talking about regression being a supervised machine learning algorithm, and our target variable, the thing that makes a regression is the fact that our target variable is continuous and there's no time involved, right? So we're moving into the modeling section of regression, and you'll notice a couple of other things going on in methodologies. One, after this, we'll get into clustering and then time series and then have an individual project. That individual project is one of your own design. So we'll talk about that as we get closer. We still have about 2 modules between here and there though. And then after that individual project, we'll get into methodologies 2, which is NLP, anomaly detection, Spark for distributed ML, and any advanced topics we've got time for, followed by the capstone. So start thinking now about your capstones. Coming up next, probably not this week, but next week, we will have the Innis folks present to y'all so that you can have an idea of what that capstone looks like, the scope, just kind of get a sense of how much work it is for a handful of people. And they're going to show off what they got to you. They're pretty excited about it. There's some really interesting projects. So for now, we're going to focus on the modeling component of regression. This is only brought possible to us by the benefit of clean data that you've already explored, right? And let's talk about our common algorithms for modeling. So rather than like 4 different lessons, rather than 4 different lessons like in classification, we're going to cover the most common regression types. One of the most common regression types that we'll talk about first is ordinary least squares. So this is what most folks think of when they think of linear regression. Now the squares here mean that we're squaring our error, our residuals between the prediction and the expected. And this is your bread and butter algorithm. It's OLS. Let's see, we've got another algorithm called lasso and Lars. It is a combination of a lasso algorithm and a Lars algorithm. So rather than distance, we're focused on at least angle with lasso Lars. Why would this be useful? Lasso Lars is performing some feature selection and some noise reduction as well underneath the hood. So don't be surprised if lasso Lars does a little bit better than an OLS, just a plain old linear model. I'm not going to go into least angle regression or what that means, or absolute shrinkage or selection operator. Right now, just think of this as another way of fitting a curve to points. Okay. If we were to take lasso Lars and set the alpha of lasso Lars to 0, it works basically exactly like ordinary least squares. And that alpha hyperparameter is anywhere between 0 and infinity. Oh, this is kind of cool. Higher alpha is more robust to collinearity between features. There's something we can do. However, as you're cranking your alpha up, it'll reach a point where performance doesn't change. And the fewer the features that you have, this is related to your degrees of freedom, the lower the value of a alpha will be for you to reach that point. So an alpha of 1 is a pretty good starting point. Why? Because an alpha of 0 is basically least squares. And this is not the same alpha as your statistical test alpha, right? We only have so many letters, so many Greek letters. If you've got a curvilinear relationship, if you've got something like a parabola or a curved line or a line with 2, 3, 5 curves, I'm going to encourage you to look at using polynomial regression as your model type. And I want to give you all a word of caution right now. A word of caution for the polynomial regression is that this is an overfitting machine if you let it be. Just like a decision tree is an overfitting machine if we're not careful. Now, how a polynomial regression works is it fits a curvy line, a polynomial to the data points. But one of the arguments that we send into the polynomial regression model is is what's called the degree. That's the number of curves in the curvy line. So let me see if I can't overfit polynomial regression. You'll see a Google search on my screen remotely. No, don't. Okay, cool. No big deal. I'll reshare that. Cool. So get a load of this. A straight on the left-hand side, a straight line linear regression to data points that go down and then go back up is not the right tool. It's not the right model. And in fact, we will be underfit in that case. Underfit is defined as the opposite of overfit. It means that your model isn't a really good explainer of the data, and it doesn't actually represent the data very well. It's not a good fit. Now, if we unbound our number of degrees, that's the number of curves on the curvy line, well, by gum, you can get a curve, you can get a line through every data point. And for a polynomial model, folks, that is the dictionary definition of an overfit linear model, is this one on the very far right? So that model is perfect for the training data, but give it something else that doesn't have the exact same slope, even if the data is similar and representative from the test or the validate set, it's going to fall on its face and you're going to have a lot of error, right? So a good measure of fit is that your model ain't perfect. Perfect models, there's got to be something going on with a perfect model. Either the target variable made it into your inputs somehow, or you're overfit, or your predictive variables are so darn good you don't even need a model. You've just got like a physical functional linear relationship or something like that between your x and your y. Is this clear on why how a polynomial could become overfit? You are in charge of that degree argument though. And I want to caution you, if you see, when you scatter plot your stuff, if you see one big curve, right, then set that to a 1 or a 2, depending on if you see little curves inside of there. But if you set your degree to like 30, you're going to get 30 turns. Yes, Vasily.
On the graph here, the bus model, it looks like 1.5. How do we determine what is the curve? Is it a certain degree threshold that we say, okay, that's a curve?
Degree, your body heat turns it on. No. If you've got, so a polynomial of degree 0 is a straight line. Degree 1 is 1 turn. Degree 2 is 2 turns. And the number of degrees, you're not telling it what like angle that degree is. It'll sort that out itself. The model will sort that out itself. If it needs to turn, or it'll figure that out itself based on the data points. The cardinal sin here, the cardinal mistake is having your degree being so high, or just making a for loop with your degree and for loop up to 100. And then, wow, I got this great model. Just don't ever look at it under a validate test, right? A validate or a test set. One of the nice things about polynomial degree argument, you have to set it, unlike a decision tree, which it just defaults to none, which is kind of dangerous, actually. Okay, so use a polynomial if you've got a curvy line, and depending on the identifiable number of curves, that's your degree. If you can't make your mind up, or if you're not sure, set it to one below and 1 above, but not like 20. Okay. Something, if you are doing a polynomial regression, we do have to transform our features, and we will fit a regression model using the transformed features. I'm going to introduce you all to one more model, and that is the Tweedy regressor. To my knowledge, no relation to the cartoon character Tweety. But this is our most flexible algorithm, and this will allow us to work depending on the power argument. We can work with normal distributions, Poisson distributions, compound distributions, gammas, inverse Gaussians, bunch of pretty wild and crazy distributions, things you haven't seen yet, so don't freak out. Okay, time to freak out now. Get it out. That was very amusing. Thank you. Ooh, it's a dry Monday morning. I like it. So we've talked about normal distributions. Those look like a bell. Those are your normal bell curve. A Poisson. We saw Poisson distributions when we had events over a time period, but that shape of a Poisson distribution doesn't necessarily have to be related to time. Compound and gammas are more exponential distributions. And then a third power Tweedy regressor can work with an inverse Gaussian distribution. I'll say that 5 times fast. If you want to know what that looks like, do a nice little Google search for it, pull up an image. And it's not the reciprocal. It's not the area that's not under a curve of a normal, but it is one of these kind of beta distributions that spikes pretty high, pretty early, and then has a tail that drags out to the right, depending on some of its features. Yeah, hey Fred.
Is it flexible enough to press like either right or left skews and have both of those?
Most likely these are going to be right skewed.
Okay.
Yeah, most likely. Yeah, we don't need to memorize all these distributions, but your polynomial is pretty powerful. But what if you have one curve, but then you have just a tail that goes on and on and on and on and on? In that case, I'd look for a Tweedy regressor and set the power to like a 1 or a 2. Cool. The pattern that we do, other than the polynomial, the pattern that we do where we make the thing, fit the thing, and use the thing is still that 3-step pattern. With polynomial, it's a 4th step because we have to fit our features with the polynomial model and transform them. So let's see how we approach this stuff. One of the reasons why you chart out histograms of your data is so you know what model might be a good model for your data, right? If you have a target variable that's not normally distributed, or a target variable that has a curvilinear relationship with an input variable, then you might know, hey, it's polynomial time. So if we have a normally distributed y and a linear relationship with our target variable or variables, we'll use OLS, lasso Lars, or the Tweedy regressor, that generalized linear model of power 0. If you have a curvilinear relationship, polynomial, and if you have any kind of distribution that looks like a stressed out normal distribution, that's really how I look at these Poisson, gamma, or inverse gammas, is they look like a normal distribution that's under some sort of compression or tension. As always, we prepare our data for the modeling itself and separate the train and the X train and the X validate, X test from the Y variables as well. Let's see. So we'll have our big data frame of everything before we split it. And then once we split, we'll have train, validate, the test, and then further separating our X and our Y. We'll need to do that. For this data, we're pulling in that some of the student grades here that we saw before. Okay, this final grade is normal-ish. It's not like perfect textbook definition. So before we start modeling, what do? We make a baseline. Your baseline is either going to be the mean or the median, whichever one's better, because all the baseline is your best guess without any other sophisticated modeling. So feel free to do both mean and median and go with whichever one is better. And then you're trying to beat your baseline. How do we know if a model beats the baseline? The model's RMSE is lower than the baseline's RMSE. Okay. So let's take a walk through this little garden of code together. We're going to create our Y-train and our Y-validate as our targets. And to produce our first baseline, we'll do G3 predicted mean. So that's Y-train on G3.mean. And then we will produce what that looks like when we set the mean as a kind of a standard value. So that's just one column where it's the mean all the way down, both on train and on validate. We do the same thing with the median. So we have two columns that are the predicted median all the way down. I want to bring something to your attention here. This is kind of subtle. Actually, it's really, really subtle. When we make a baseline, notice we're not going off of the population mean or the population median. Did anybody catch that? We're going off of the train mean and the train median here. So I'm pretty sure in classification, we didn't do a song and dance about it, but y'all still, in your computational steps, made your mode off of train. So same thing here, right? We don't want target leakage from the out of sample. Okay. So we'll calculate the RMSE of, because we know that models aren't perfect. So there's going to be some error. We check the RMSE on train, RMSE on validate, and that's of the mean. Then we check the RMSE of the median on train and validate. And as we zoom in here, we see our RMSE, which is the square root of the sum of all of the square root of the average value of all of the errors squared, right? Why do we square our errors? Anybody know why we square our errors? Andrew?
So there's a lot of negative and positive. Makes it all positive.
Our error squaring makes our errors all positive. That is one thing. We could also take the absolute value for that. Anybody want to add to that? Tack on, Fred?
It can clarify like which model has higher error. If you look at pretty small numbers, it's going to be a bigger distribution.
Okay.
It's like
You mean like the magnitude of the error?
yeah.
Yeah. So if our error is high, like if our error is low, like 0.0001, the square of that is very small. The square of 1 is 1, right? But when we get to things like larger numbers, like 9 or 100, when we square them, they grow very, very fast. So when we square errors, we're penalizing farther away errors at an exponential rate, actually. And then we take the square root of the mean squared error to go back to the same original units. So if these units were in points out of 100, our RMSE is in points out of 100. If the units were dollars, our RMSE is dollars, which is really nice. It's tough to explain model performance in terms of square dollars of error. Square dollars of error. Yeah, nobody wants to hear that. They want to see, is it a good model? Yes, chef, it's a good model. Cool. So we do have, you don't have to necessarily always build two baselines, but keep in mind that median and mean are basically trying to measure a very similar thing. They're trying to get to know the middle of a data set, and means are more sensitive to outliers, right? So if you want to be less sensitive to your extreme outliers, use median. That's why we use median when we talk about things like home prices or income levels, right? We might use average for things that are like body weight, right? We have some extremes, but not like millions of times more extreme, like more unbounded, exponentially growing things. So I've got a little visual here. Basically, all this is doing is showing the actual final grades as a distribution. That's the blue histogram. And then the orange and yellow, those are our vertical lines that are showing a median and a mean, respectively. And the orange and the yellow have or like a red and a yellow have an orange in the middle because they've got a little bit of overlap there. It's just a function of the width of those. Okay, so we've got a baseline. It's not perfect. We're not capturing everything, and there's a bit of error here. And that error, 4.5, 4.58, doesn't seem too big. But then when we look at the final grade going from 0 to just shy of 18, that's a pretty big variance, right? That's like a quarter, more than a quarter of the values are contained in that error. So let's take a look at using a linear regression to see if we can beat our baseline. How do we create a linear regression? Folks, it's real methodical and algorithmic. You make the thing, you fit the thing, and you use the thing. So here's how we make it, here's how we fit it, here's how we use it. We'll call the linear regression model. Normalizing is a good thing, so we'll set that to true if it's not defaulted, that hyperparameter is not defaulted already. So we make our empty linear model, then we fit the linear model on the training data set. The first argument is the X, and the second argument is our target variable. Okay. In this one example, Y train happened to be a data frame, not a single column. That's why we're calling a column off of that data frame. And then we will use the model to make predictions. So lm.predict on X train, we now have the model's predictions. What are the model's predictions? Well, the model's predictions are formed by the model's slope and intercept. That's really it. That's really all a model is. A linear model is a slope and an intercept. And if it's a fancier linear model, it's a slope and an intercept with coefficients. So how exciting is this? It's like the most boring line of code in this entire lesson. And you're just doing machine learning modeling, no big deal. So make the thing, fit the thing, and use the thing. Once we've made predictions using the model, it's now where we want to calculate, use the mean squared error function and take the square root of that. So the mean squared error function is built into sklearn. And what it is doing is taking the difference of every data point between these two series, squaring the differences, and then summing them all up together and getting the average of that. And then we raise that to the 1.5 power. What does raising something to the 1.5 power do?
Square root.
Takes the square root. Don't let that slow you down. Fractional exponents are roots. Yeah, it's a thing. I didn't invent it. So we will get our predictions for Y train. We'll also get our predictions for validate. Notice we are using the model trained on train to make predictions on validate. That's how it works. Right? Always train on train. And then we'll calculate our error from there. And what we see is OLS using linear regression. Our in sample is 1.75 units of error. So whatever grade that is. And the out of sample is it's overfit, right? I can't tell you how overfit because this isn't like giving me, it's not twice as much error, but it could be kind of crummy. We'll have to run some more models to find out. But right out of the gate, both of these are better than guessing the median or guessing the mean. So it makes sense to use this model or make other models to see if we can beat this one. Questions so far? I'll pause and give y'all a chance to digest and really think about what we just did here. We're definitely overfitting, but we're still doing better than the baseline. So we'll keep on keeping on with the modeling. Let's move forward and use a new model called Lasso Lars. Okay. And so Lasso Lars has a hyperparameter called alpha. If your alpha is 0, it's identical to OLS, the model we just ran. And that alpha can go from 1 to infinity, and it's going to cap out. It's going to reach a limit for its usefulness. Yeah.
You're running it for graph worlds with multiple alpha, or you've already done it like you're spotting the distribution, your binary.
Yeah, you totally could. You totally could crank this out in a loop, but don't be surprised if that alpha is going to be real low. Because it's a function of the number of columns you have. So if you have like 10 columns, I don't think your alpha is going to go do anything for you above 10. It's not a one-to-one relationship, but it's a function of the columns because it's a function of degrees of freedom. I'm relatively certain mathematically. So we make the object. In this case, it's a Lasso Lars model. So it's a blank model that all it knows is its alpha is 1. Then we train the model on the training data set, the X's and the Y's. We send in X's because that's where it's making its predictions. We send in the Y's so it has some labels. And then we make predictions. Then we'll evaluate those predictions. And interestingly enough, the RMSE for Lasso Lars it's worse. So I have higher amount of error for Lasso Lars. It's less overfit. In fact, it's a tiny amount underfit. But these numbers, 4.5, are much closer to the mean, right? That amount of error is closer to the mean. So let's see what else we can do. Let's bring in our good friend Tweety regressor. And with the Tweety regressor, you could as well experiment with the power and the alpha on here. Really, the power is telling the Tweety regressor what shape of distribution we have. But Tweety is pretty neat because it can, with the right arguments, it can do what a lot of our OLS models can do and our polynomial. So we'll make the Tweety regressor, we'll fit the Tweety regressor, and we'll make predictions using that Tweety regressor. Once we have predictions, we will use those. We calculate the mean squared error of the real versus the predictions, take the square root of that, so we're getting back into original units. We'll predict validate as well, and we see, Tweety regressor, in sample and out of sample, it's a tiny bit overfit, but it's doing a lot better overall. So it's 2.18 grade points and 2.38 grade points. And given that it's less overfit than that first linear model, I feel more comfortable with it. And we can keep going. We can keep playing with the power depending on our distribution. But that's a pretty good sign when you can have your errors for in sample and out of sample both be pretty low, and they're both better than baseline. You're in business. You're in business. Okay. Yeah, Angela. Let's find out. I don't know off the top of my head. I don't think it does. Well, let's find out. So power is set to 0 automatically, alpha is set to 1 automatically. There's a couple of other hyperparameters, which I think the defaults are fine for. And power set to 1 as Poisson. And that's interesting. If your power argument is between 0 and 1, non-inclusive, that means no distribution exists. That's kind of crazy. There's not a named distribution that follows. I hadn't considered that before. So your question, D'Angelo, is the alpha the same thing? Constant that multiplies the penalty term And this determines the regularization strength. I think this might be the same thing. Let's check it out. Let's check out our Lasso Lars. This is a constant that multiplies the penalty term. Okay, they're both penalty terms. Defaults to 1, 0 is equivalent to LLS. For numerical reasons, using alpha 0 is not advised, and you should prefer a linear regression object instead. So this is multiplying a penalty term. This is multiplying a penalty term. So yeah, they're both related to regularization as well. And regularization is a way of the model having some ability to keep itself from being overfit. It's not perfect, but.
So then in that case, because it was still a little bit.
Yeah.
So many people said it's less.
Oh, if you change your alpha? Yeah, you can play with that for sure. You can change the alpha, you can change the power. Yeah. So far, I've talked about 3 models: the Lasso Lars, the OLS, just the straight line linear regression, and the Tweedy regressor. All 3 of those have followed the make the thing fit the thing, use the thing. What's going to be different for us in this space is the polynomial regression. So let me introduce that to you. So what we do is we create our new features. And then we fit the linear regression model. We predict using the transformed features. We evaluate using an RMSE. We repeat our predictions for evaluation, and then we compare our RMSEs from validate and train to see if we're overfitting. So when I say we're transforming the features, what the heck does that mean? The pattern here is going to seem very similar to a scalar. So what we do is we make the polynomial object first. So PF, your variable name can be something else, but make it explanatory. Notice then we take that empty polynomial features object. Notice this out of the gate is not a polynomial model, it's a polynomial features object. And then we fit transform train. So we're basically transforming our features through this polynomial function. And then once we have fit and transformed our data, we get a new data frame. Keep this data frame separate in its own variable. You don't want to overwrite your X test by accident. That would really be annoying for your troubleshooting if you try to polynomial in like 10 other models. And then we'll transform validate as well. And we'll transform test as well. And then let's see, LM2. And then notice how we have transformed features. We make a plain Jane linear regression and we fit it on the transformed features. So this is a little different than make the thing fit the thing, use the thing. It's kind of like, it's a little more like scaling because we're transforming our features. We're polynomializing our features. I don't think that's a word. And then everything else is the same. Once you have your linear model, you train it on the transformed features, make predictions, and then calculate your error. And I see a question from Arsene. Go ahead, Arsene.
So I'd assume the degree is the number of features, but is it where the use of the eval that we did kind of shows its usefulness, because we saw that we can kind of rank the features, so we could use that as like a degree determinant
Let's talk about that degree and how to determine what you want your degree to be.
Okay.
So visually, a degree 0 is a horizontal line.
Oh, I see.
Degree 1 is a straight line with some slope. Degree 2 it's basically like n-1 curves, right?
Mhm, mhm.
So degree of 2 has two arrows and 1 curve. Degree 3 has 2 curves. Degree 4 has 3 curves, et cetera, et cetera.
Seems like so, right, with like line that's square.
Yeah, because polynomials
Yeah.
look
Yeah.
like that. Cool. Was that helpful, Arsene?
Oh yeah. It
Okay,
was.
question.
Yeah. I didn't even think about it. I thought I was more thinking about the parameters. Thank you.
Got it. So this threw me for a loop. The first time I tried to use a polynomial model, I kept searching the sklearn docs for the polynomial model, when really we have to go out of our way just a little bit, transform our features with the polynomial feature transformer, and then we'll use those transform features. That's what this X-train degree 2 is. So you'll have to make a data frame for each degree of polynomial you want to check out. So if you build this in a for loop to check like 1 through 10 degree polynomials, you'll probably want to be making some new data frames. Let's see a question. Me too. You have, instead of having, let me take it from the top, the last like paragraph or two. The polynomial features is not a model. Really, what we're doing is transforming our data so that we can use the linear model on those transformed features. Okay. And then we'll plot everything out. If you wanted to plot out your actual versus predicted, see where our predictions are more extreme, right? We totally could. Let's see. So the actual versus predicted, if the ideal line here, this blue line, would be if you had a perfect model. All of your predictions were in fact accurate. So if we see that one of these color models is trending more tightly around this line, that's a good thing. That tells us that model is pretty good, right? I'm noticing maybe it's just my eyes, but it seems there's a little bit more green closer in, and there's a bit more red and yellow further out, which kind of tracks with our polynomial doing reasonably well here, actually, even on that sample. And then we can plot the errors themselves and see if our predictions are predicting high or predicting low or predicting evenly high and low, because we kind of want them predicting evenly high and evenly low. And it's all about that RMSE, right? I realize we had a number of metrics, and I want to speak to this. We had a couple of different metrics in pull up my Sublime here. And the model evaluation, we could use mean absolute error. That's just the absolute value of all the errors. We could use the mean squared error. And then there's the root mean squared error. And this is like, oh my God, which one of these do I use? These are much less of an issue than accuracy versus precision versus recall. There's no confusion matrix here, but with mean absolute error, we're just taking the absolute value. So we're not penalizing farther away predictions. That's all that's going on. I'm of the opinion we should probably penalize our poor predictions. So mean squared error is a good tool. Mean squared error gives you back errors in terms of square millimeters or dollars squared. So take the square root of that and basically, like my opinion is use RMSE until somebody pays you not to, or makes a compelling argument not to, right? I wouldn't say that about classification because accuracy wasn't everything, but these are all different ways of measuring or penalizing the residuals. That's it. And the residual is the difference between the data point and the prediction. Okay. So you're going to see RMSE a lot more often. So if you're building out a whole bunch of different models and predictions, just focus on RMSE. You're not going to win the state fair by splitting hairs on MSE versus RMSE. And then looking at these exercises real quick, they're a very robust exercise set. There's 3 bullet points there. Select a data set with a continuous variable. I'll give you 3 guesses what that is for y'all. Be sure your data is prepared. Y'all have already done that. Work through all the steps. So the exercises here are really to just make a model and evaluate that model. And with that in mind, I want to give y'all some time to crank that out. I'm thinking in like half an hour, 45 minutes or so, we'll kick off the project proper and deliver y'all the rubric so you know how things are going to be graded, all that good stuff. And then we will start the project proper. Lincoln, did you have a question?
I see that earlier when you used the scale data, and also kind of scale it later on. So in the beginning, should we use the scale data, the scale training data to
Yeah.
do all this? Okay.
Yeah. Yeah, your algorithms are not going to stop you from using unscaled data. Just a human being will, right? But you will have more interpretable models. In some cases, you will have more accurate models with scaled data. But definitely you want to scale for a handful of reasons.
I didn't realize this one, it wasn't scaled, so that's why I was wondering, like, what should we, at the beginning, it was just numbers, right?
Yeah, you know, scale your business. These, I think I only used one value, so I didn't have to scale. If you only have one input variable, you don't have to scale it. Cool, cool, cool.